Okay, good evening everyone. We might make a start. So welcome to this Energy Express seminar. My name's Chris Gregg and I'm the Director of the Dow Centre and the UQ Energy Initiative. Just some housekeeping to begin. So there's no fire alarms planned, so if there is a fire alarm, you'll follow us out this way and onto the grassy areas out there. On behalf of the university, as always, we acknowledge the traditional owners of this place in which we gather and acknowledge their elders past and present. Tonight we will have a talk from Dr. Xu. He will speak for at least 45 minutes, so it's a fairly long presentation, and then we'll have Q&A for perhaps 15 minutes. But we do have drinks and nibbles afterwards, and we would encourage everyone to continue outside with us and network. But we'll quickly get into Dr. Xu. Dr. Xu is the Chief Technology Officer for NICE, the National Institute for Clean and Low Carbon Energy in Beijing. It's an industrially focused and funded research institute that looks at a broad range of energy solutions. Has an annual budget of about $120 million. Dr. Xu comes from a long career. He started as a chemical engineer with his PhD from Berkeley, UC Berkeley. He worked in the US for some time for a number of chemical companies. He has a number of patents, including for a particular olefin that has sold hundreds of millions of dollars worth, or billions of dollars worth of revenue, and made a very substantial profit. So one of these rare people who has made a real effort and a real success, commercial success with technology. He's also spent part of his career in Singapore, so from the US to Singapore, and now was recruited back to China to lead the technology operations for NICE. So without any further ado, I'd like to hand over to Dr. Wayne Xu.
Thank you, Chris. Can you hear me all right? All right, good. I thought that it'd be good that for me just to talk about a little bit of the research work that we conduct at NICE that is really trying to help China moving towards a clean energy future. Let me give you a brief introduction about our parent company called Shenhua. Shenhua is one of the largest energy provider, particularly in coal area, that we supply lots of coals for China. On an annual basis, Shenhua produce about 500 million tons of coal. Put that into perspective, it's a little bit more than what the entire Australia was doing. The other thing is that we also is one of the largest power generation companies that we generate about somewhere around 80 gigawatts of electricity on an annual basis. Also slightly bigger than entire Australia. Australia is somewhere around 60 to 65 gigawatts. We also have a business in railroads and also coal to chemical. We are also one of the largest coal to chemical company in the world. In terms of profit, last year we making somewhere around 6 billion euros profit. That gives you, a brief background about Shenhua. NICE is the corporate research arms for Shenhua. We are in the process of transforming into a world-class clean energy, from coal-based into a clean energy company. So I thought I will give a talk divided into 3 portions. I will briefly give outlines where we are in terms of the China energy overviews and also some of the grand challenges that face in China in the energy sector. And then I will also mention a little bit about our NICE strategy that was aligned, from technology standpoint of view and trying to address those big challenges. And in the part 2, I will exactly talk about what exactly we do in terms of research and R&D and the demonstration. And finally, I will have a summary page. So we all know that China had a rapid, very, very rapid, economic growth for the last, at least, say, couple of decades, right? I will just highlight a few of those things here. One of the things that you look at the number of private vehicles, the passenger cars. Right now, it sits somewhere around 120 million. 120 million, private cars. And you're talking about the Australia population is about 23 million. So in other words, everyone maybe have 5 or 6 cars. That's how much cars that you have in China. And also you look at the population, the urban population in China, right? This is the proportions, right? It kept growing. Right now we're talking about somewhere around 800 million, people it's living in being urbanized. So that's a staggering number. It's a huge number. Not to mention the railway lanes and also the highway lanes. We're ranking the number 1 in the world. So that gives you a snapshot of what we're dealing with, right? And then the other thing, you look at the GDP growth in China for the last in a couple of decades. But that's really fueled or supported by the energy production and also the energy consumption, right? But you also notice that there's a gap in between the consumption and the production. But that's what those imports, particularly a lot of those energy was imported from Australia. So that fills that gap right here. So you're looking at the 2014, the energy production in China, it's somewhere around 3.6 billion tons of, standard, equivalent coal, right? And consumption it's a bit higher than that number. So that gives you a magnitude that what we're dealing with in terms of the energies, the size of that. Now, the other thing also we need to keep in mind is the population growth, right? China was projected by the year of 2020 that we're going to have 1.45 billion people living in China. So you have a GDP growth, you also have a population growth, so that's really driving the energy demand, So you're looking at this thing here, chart here, with the GDP growth and also population growth. So by the year of 2020, we're talking about 5.5, billion tons of standard coal. So that tells you where we are in terms of energy demand. Put that into perspective, okay? So from the production side and consumption side, both we far, past the number 1 economy in the world, which is USA. So we far exceeded that number. So if you're wondering where's Australia, so Australia's right here, okay? So even though the Australia production is more than they consumed, so I imagine, a lot of them was exported to China, to Korea, and so on and so forth, Asia countries. So that's what we are talking about, right? The other figures I want to also mention that China uses a lot of energy, but for the energy intensity, there's a big gaps here, okay? What does that really mean is that we're looking at, you generate the same amount of GDP, okay? For example, in this case, $1,000 US dollar. But China uses much more energy to generate the same amount of GDP. So that tells you that we are not efficient. So that's something that we could do potentially, by improve this number that you could reduce CO2 emission and so on and so forth. But I'm putting this one here. Now we understand the magnitude, the energy mix, everything here. So we needed thinking about the, coal remains to be the dominant source, right? You look at this energy mix here, right? We, in China, we got lots of coal reserve. Very, very little on, in terms of oil and the natural gas, right? And that's the nature of the beast that we're dealing with right now. And also you look at the investment installed, coal-fired power generation. Look at those red ones. But that's from China, right? A lot of them are fairly new. Some of them even less than 5 years. A lot of them is 5 years old, right? You're building a lot of, facilities for the coal-fired generation. So what does that really tells you? It tells us that the coal is here. It's not going anywhere. Well, you would think, well, you listed those fossil fuel here. What about the renewables? What about the nuclear, some other things? So right now, the nuclear and the renewables, you all added together like hydro, wind power, and solar. It's less than 10%. It's fairly small amount of the entire energy mix. Even though China trying to, increase that, but it will take time. And not to mention that some of them are not that cheap, right? Okay, now, however, there's a problem, right? We all know that this emission that are associated with coal, that tells us that, in terms of the percentage base, right? And, look like SOx, NOx, and CO2, percentage-wise, this is what's the percentage, come from coal. So larger portion of, look at the SOx, about 90% of the SOx generated in China is from coal. So that's the issues that we are on hand, we have to deal with. Not to mention that the CO2 emission factor, coal is much higher than oil and natural gas, right? So then you go a little bit further, you talk about the PM 2.5 mortalities, right? You also look at the number, about 40% of that was associated with coal, right? Here's the number that in 2013 that generated by the global burden of disease. They have a number saying that have 40% of mortality that is associated with coal because of this PM 2.5, right? And the other thing that we have to deal with is this water stress. Yeah, you look at the energy, what we are dealing with, that you always associate that, energy, water, it goes hand in hand, right? You look at a lot of those coal-fired power plants. I was surrounded in an area that was red, right? That's the area that you really have the energy stress. I mean, the water stress, water tension, right? So maybe I'm too far away from they couldn't get me to. So what this really led to a number of grand challenges. So I summarized here a few of them, right? One is that what we call the energy security. Energy security means that you have a continual population growth. You have per capita, energy intensity, right? That means you consume a lot of resource, right? And then also you can see that the import dependency. You take a look at oils, almost close to 60% of oils we're importing, right? And the air quality issue and water stress issue. So I put a number here that it is 23 million Chinese lives in the area. PM it's exceeded 100, right? So water stress, particularly in the northern region, northern provinces of China, right? Also renewables, in order to resolve some of this resource issue, you also want to look into, you want to get renewable onto the grid. Well, there's grid stability issues, right? And then also not to mention that it's much higher cost than the renewables. No one says that the renewable is cheaper, right? I'm not sure that a lot of people are might thinking that, the renewables is cheap, right? Like sunlight is much cheap. But when you're converting into electricity, it's not that cheap. And not to last and not least, you have this carbon emission issue. And here's a number that, on the 2014, China is emitting somewhere around 10 billion tons of CO2, right? That's a big number, right? So you want to go a little bit further than talking about the challenge number one. I mentioned that you have oil, right? It was really import a lot of them, close to 60%. So you're always thinking that, we do have a lot of coal. Can we unlock the value of coal? Maybe you can make coal to oil. That would be somewhat energy independent, so that we won't be really depending on imports a lot. Maybe coal to chemicals. That could be something that we could do. All right, maybe I would just too far away from the computer, they're nothing. Okay, now the number two challenges, right? We're talking about here. We got a lot of people living in an area that was, much higher PM 2.5. By the way, Beijing had about 23 million. Beijing barely made it to that number. Beijing's on the average is about 90. PM 2.5. But now I want to put that into perspective. You look at the World Health Organization guidelines, actually it's 10. But since China is far away from it, so they give us another one. So, if you can't get to 10, can you get to somewhat the interim target, which is 35? Even 35, we have a long way to go. Right, that tells you the things that we're dealing with. And some of you might not really knowing what this a haze looks like, right? I want to just give you somebody took this for me and just give you so that's what we're seeing, okay, in Beijing. Now, the other thing is that also water, you look at the underground water, a larger percentage of underground water is either rated bad or extremely bad, it's close to 60%, right? So that's an issue. That's something that we have to deal with, right? And then what are we going to do? Can we do something can we really get to zero discharge, on those, coal utilization, right? Now, what about the renewables? Like I mentioned that, China really wants to get, coal and hydro and solar and wind all maybe integrated together. But this is a challenge. The challenge is that you have those renewables that you encounter those intermittency issue, right? You also look at this thing, high curtailment ratio in the northern part of China. That's where you got a lot of sun energy, solar, you got lots of, wind power. It's most of them are sitting here. And then you cannot get onto the grid, cannot get online, and a lot of, some regions, the curtailment ratio as high as 40 to 50%. So that's not easy to resolve. So the question is that how can we get it from here to there, in terms of cost and grid stability, right? Those are the challenges that we are facing. Okay, again, you're talking about CO2, right? I mentioned that we are somewhere around sitting on 10 billion tons of CO2. That's a large number. And you're talking about the, Paris Agreement, by the 2030 and 2050, there's a huge reduction. And people argue, well, by then, is China, by the year of 2050, is China going to be a developing country or a developed country? But either way, okay, if we join the rest of the developed country like the U.S., so we all added here, but this is a number 25 here. If we are still as a developing country, it's 88. Either way, it's a huge reduction that we have to do. So that's the issue, that's the challenge that we're facing, right? So we think that the technology can play a role. This is a tremendous opportunity for innovation. So that's why we at NICE that we have 8 platform that was designed to address those grand challenges. Like we have a platform called Catalysis, coal-based materials, water, clean coal, solar, distributed energy, all the way to advanced technology on carbon management, all the way to hydrogens. I will elaborate a little bit more further. So this is the platform that we are having, right? We are making the big bets. So that's what we are trying to focusing on. What do we think that we can do to really help address those grand challenges? For example, like water, right? Can we really do a wastewater at no discharge? So this is something that we want to take that challenge. On the CO2 side on the CO2 emission reduction, right? Can we really make it at least affordable? Right now it's too expensive, and solar is the same way, Can we do it with great parity, Right now it just costs too much, right? Can you do it without government subsidize it? So those are the things that we do. Of course, we also have quite a few platforms related to addressing the coal issue. For example, like safe and efficient clean coal utilization process. Can we develop a process relates to that, right? And also upgrading, coal products, right? If you use coal as a raw material, can we really add values to it? So can we do something that can really be valuable, both the organic compound and also inorganic portion of the coal, that maybe we could use it for something that really have a higher value. So I won't go through each every one of them, but that comes to my second portion of what we do here. So what I will do is that we'll talk about those platform linkages to those big bets, and give a outline of a strategy, what we do, and then highlight some of the technologies. So, like clean coal. I mentioned that, coal is not going anywhere in China in terms of the energy mix, So we really have to do something about it. Can we make it clean? So you look at the coal, right? You have 80% of them, at least in China, the coal is for combustion purpose. Majority of them is for power generation. And then also you have a small portion, it's discrete use for smaller, energy, industrial boiler and some residential applications, right? And then you also have a portion that is for making cokes, coking that. That's for iron and steel industry. And then you also have a 5% for gasification that you make syngas. Now ultimately syngas can convert to oil and the chemicals. So that's what we do. So then we have to address the emission issue. So that's why you will look at it. If use coal as a fuel, we develop a technology called ultra low emission, ULE, fire power plant technology that involves DeNOx burner and SCR DeNOx technology, all the way to wet and dry electric precipitate technologies. Now you look at this chart here that for the national standard that for natural gas, right? This is for natural gas. Here's the standard for soot and SOx and NOx. But also you look at Shenhua, a lot of them are meeting the standard, actually exceeded the standard of natural gas. So what does that mean? It means that we really have a technology, can be as clean as a natural gas power plant. So that's pretty good. Particularly you look at the Shenhua's demos plants, right? All those numbers much lower than the standard. And at this point that we, like I said, Shenhua generated about close to 80 gigawatts. And 65 of them has already converted into this new technology. So we develop a technology like that. The other thing is that you use coal as a fuel. That I mentioned that you have some discrete use. But those discrete use, you might not have the luxury, you have a DeNOx burner, you can collect in those, SOx, NOx, and dust, and so on and so forth. So what we did is that we have a refining process. Can you get rid of those things before that you get to the combustion for the discrete use? So we have a process we call pyrolysis, and trying to remove those, some of the SOx and NOx, particulate, and also get rid of mercury, and then you can. After that, it's much cleaner. So you look at those upgrade ones, mercury you can reduce a lot, sulfur and volatiles and so on and so forth. So by way of you clean it up first, and then you can use it as a discrete use for combustion. So that tells us that what are you going to do, in terms of addressing the clean coal issue. Now we also talk about can we also converting the coal to some other oils and chemicals that maybe could help addressing the resource issue that's really a challenge to us because of the population growth and because of the per GPT per capita energy intensity growth. So we have a gasification process. The majority of our gasification process in the catalyst area that we're focusing on the two routes. One is the Fischer-Tropsch, and it goes through the hydrogenation. You can produce fuel and chemicals. The other one is we follow the methanol economy, and we produce methanol and to olefins. And for the combustion side of it, we also develop a catalyst for power plants for reduce the SOx. So I will also highlight one of the technology here, and it's called iron-based Fischer-Tropsch catalyst. But you look at this this table here, that compared to the competitors, many of our performance much higher, including the yield and also CO2 selection, all the way to the attrition rate and to the bulk density. So we have an advantage on that. Like I mentioned, that Shenhua is one of the largest coal-to-chemical, coal-to-oil producer in the world. So we certainly own technology in this area. By the way, the other country that was doing good is in South Africa. Sasol used to do a lot of those process because of the apartheid age that there's oil embargo. So it forced South Africa to thinking about energy independent, and they happens to also to have a lot of coal. So they also trying to do a process. But ours is much bigger than South Africa right now. The other way that we have to use coal as a resource, as a raw material. So that's how we also trying to address this energy and also resource scarcity issue. So can we upgrading coal products to high end? So basically, you use coal as a raw material, right? Initially, we all thinking about resource driven. What do we got? We got a lot of coal, right? Maybe you can go through the power plant. You have a lot of fly ash, and then you also do gasification. You can make MTO out of it. You can make olefin out of it. You can have a lot of polymer. And also we have liquefaction, direct and indirect liquefaction. You're making chemical and also some residue out of it. So what we do at NICE is that can we do a product extension? Can we increase the value of the products? So it's more of focusing on, you have a product extension and adding values to the products. So more towards innovation driven instead of resource driven. So that's what we do. We're trying to do work in that area. So I will also give a product, technology highlight here. So what we are having here is that we have a cross-linking, polymer cross-linking technology that encompasses that we have an initiator, you have an inhibitor, and also have some cross-link promoter, all the way to some process aid, all mixed together. That we have this know-hows that basically allow us to delay the cross-link temperature, that allow us to process it. In other words, the viscosity won't raise up too fast, too quick, so that you won't be able to process. So it allows you to process it, but yet, in the end, you really want them to cross-link. After you cross-link, it really gives you a lot of good, properties that we really like high toughness, high stiffness, so on and so forth. So that's the technology we developed at NICE. And we actually have formed companies just to market this technology. Now, come to water part of it. Again, like I mentioned, that the energy and the water, they're just like twins. They're associated with each other. There are lots of energy, generation process. You name it. Coal-fired power plants, mining the coal. They all involve all kinds of lots of water. Not to mention that the coal to chemicals, coal to oils, also is a water intense process. So can we really do it in wastewater at no discharge? So we developed a whole host of technology just to try to address that issue. So we built a unique technology portfolio on the zero liquid discharge. So basically what we are talking about here is that, the toughest part of wastewater treatment is those total dissolvable solids. The organic portion of the solids part of it, you probably could be fairly easy to get, either filtrate them out or some other oxidation or some anaerobic process. Those is all traditional. It's technology is mature. But it is the salt that is being dissolved into the water that's tough. So we have a process like this. Could be one of them called ambient temperature crystallization. Other ones be low temperature crystallization. We develop a lot of those technologies around those areas, trying to address this issue. Our thoughts behind is that we are slightly different than the traditional ones. Traditional thinking is that we always want to, take the water out of it, by, maybe evaporating them. That actually is energy intense. In other words, you are involved this phase change, from liquid to vapor. So that's energy intensive. Our thinking is that, well, maybe we should not involve phase change. Maybe we could take the solids, crystallize, take them out from the water instead of you take the water out from the salt. So that's our thought. That's why we develop technologies involved in how you can do crystallization, how can you quickly and fast remove those salts. Now, here I also want to highlight a couple of technology here. So you look at, you have the majority of the salt. It's, either your calcium, you're dealing with a sodium ion, and it would be sulfide or chloride. That's the most abundant, species on Earth. So pretty much everything else you could either get rid of or maybe converting it into this form of salt. So what we do is that we have some anti-scalants you add it to here. You get to this reverse osmosis process that you can have the water comes out. But yet, because of you add those anti-scalant to it, so the water at this point, it's super saturated. But the anti-scalant, just like a chelating agent, that chelates the calcium ion, so they won't allow the calcium ion to be precipitated out. But then after this process, you reach the supersaturating stage, and then you add some coagulants to it, so kind of remove this chelating agent. And then by that time, you can also add some calcium sulfide as a seed to crystallize it. So it's easy. That way you can get the sodium calcium sulfide out. So then you get to the next stage, and now you get to the nanofiltration stage. Now the nanofiltration will let the sodium chloride pass through. But because of the sulfide ion are so big, so they won't allow them to go through. But we also know that the sodium sulfide it's quite soluble in water at higher temperature. But they're very, very sensitive to temperature change. In other words, when you drop the temperature, the solubility dramatically reduced. So that way you also are trying to reduce the temperature, and then you're trying to crystallize the sodium salt. So that way you separate those three salts. So that's the technology that we develop at NICE. So I won't go into a little bit any more details. So up to this point, we are trying to address this resource scarcity issue. Energy, issue particularly relates to coal, right? You have the emission issue. You have the converting coal to much more useful products, and now it gets to the new energy area. So we have a platform called the distributed energy. So in this platform, majority of our work, our key work relates to this energy storage. Can we really make it economically viable, right? We all know that right now it's too costly. It's difficult to deploy it in a big scale, right? Even though guys like Elon Musk are also trying to do something about it, but it's just too costly. For a market to adapt into the grid system, we got a long way to go. So you look at this thing here, right? You have a centralized grid. I think this is, the grid system in China. Just look like that. But it is higher carbon. Now you want to get to low carbon and distribute it. You're trying to integrate, those renewables into it, right? Certainly, the centralized high carbon grid system, it's low cost. That you have them, a lot of them built-in attribute, but you do have an emission issue, right? So then we want to get into solar and wind powers, but this intermittency issue, it's right there. So we think that the energy storage is one of the key enablers. So that's why we're focusing on that. Now, I'm not going to talk every aspect of the energy storage. I only highlight one of them. Here is that we certainly do a lot of the electrochemical energy storage. People talk about, molten salt. You're talking about, pump hydro, so on and so forth. So I highlight some of here on the electrochemical energy storage, right? You have some technology, it's reaching the mature stage. Others is in the developing stage, and some of the trending, right? You look at this thing here, all of them are really high cost. Could easily be $500 or even more, right? But he really wants to make it a larger scale. You have to get down somewhere around maybe close to 100, right? So there's lots of work that need to be done, right? So you look at it, evaluate it, some of them might have some potential to get down to 100, 200 range. So this is some of those technologies that NICE has been trying to focusing on. Can't do everything, but we selectively do some, right? And here I also highlight one of the technology that it's on this low-cost flow battery. And right now you can see, right now it sits around somewhere around $700 to $800, right? And also the power density is kind of low. So we also demonstrated something that we could easily reach to, 300 to 800 in range and much more cost effective. So that's the technology that we are trying to do at NICE. Solar, I mentioned that can we do something that you can really reach this grid parity? We choose one of the technology called CIGS. We evaluated, the silicon-based, the CIGS, cadmium telluride, so on and so forth. But in the end, we choose a CIGS technology. And last year, Shenhua invested $500 million into this program. So basically, we still need to improve the efficiency. How you're going to get the conversion rate, from solar to electricity, and then also the materials development. Can you really reduce the cost? And also the other ways that maybe you could commercialize. You really get the economies of scale up. Maybe you can reduce the cost that way. Also, I want to highlight one of the project here. In the lab that we have developed a project, a process called the post-deposition treatment of CIGS, that in the lab that we demonstrated there could be a 2% of efficiency improvement by treating the potassium ion. That's what we are trying to do in a demo unit. By the way, the 22.6, that's a world record, and we hold that record. So by putting the potassium ion layer right here, that it actually create what we call a quasi-homo p-n junction that really allows the electron to move around much quicker, much faster. And also it reduces cadmium sulfide buffer layer that also allows those short wavelengths of the light gets into this absorber layer, which is increase the efficiency for the absorption. So that's the technology we do. And we also have another platform relates to the hydrogen. So we like to see the hydrogen mobility for the big mass transit. Everybody can access using it. So in this platform, our strategy is focusing on the production side and also storage and transport, all the way to the filling station to the fuel cell devices. For example, like the production side, right? We could use renewable to generate hydrogen. You also could use some electrolysis process, particularly from those curtailed wind. You have abundant electricity, and also coal to hydrogens, maybe with CCS, the storage, right? All the way to some other storage and transport. And storage and transport, hydrogen it's been so light, from volumetric standpoint of view, the energy density is not that high. So we need to figure out how we can have a high density of storage. That's what we do. So all the way to a filling station, we develop dispenser controls, how you can, really develop the algorithm, allow this filling station can function to fill the hydrogens into our tanks, all the way to the fuel cell device, right? So I also will highlight one of the technology we are looking into it. It's called the liquid organic hydrogen carrier. So basically, you have a compound that you have a double bonds, right? And then you figure out ways you add hydrogens to it, use a catalyst, and then you create another compound that without double bond. So then you ship this thing, hundreds, thousands of miles away. So as a hydrogen carrier, they carry hydrogen. And then when you reach the destination, so right, you have another, catalytic process, release the hydrogen, you dehydrogenate it. And then you come back to this original compound. So you can recycle it so many times. That way you can reduce the cost. Right. The problem is that you have a stability issue and also kinetic issue that we're dealing with. On one hand, you really want this compound to be stable so that you can go so many cycles without generating any impurity of it. But any stable compound like this one here, this is, by the way, called dibenzyl toluene. You really need a lot of energy to remove this hydrogen once you reach the destination, right? You're talking about here 65 kilojoules per mole. But hydrogen itself is about somewhere around 180, 190. So in other words, 1/3 of the energy you already expended just by doing this dehydrogenation process. So we're thinking about, well, maybe there's some kind of kinetic we can do, or maybe develop some kind of catalyst that could allow this in a bit easier. So you can introduce some other compound. So we're looking into some compounds like carbazols, some other stuff that but you ran into issues, either kinetic or stability issue. But more research is needed in those areas. All right, and carbon emission, last and not least, you get to this one. The carbon is there, okay, particularly in China, because the coal is one of the dominant source of energy for China, at least for the foreseeable future. So then we have to figure out ways how to do it. So what we are trying to do here is that, well, maybe you could you look into the cost contribution of the CO2, right? We take a look at it. Can we make it affordable? So maybe we can look at it maybe on the capture side. Is there any ways that you could do a capture that's much more cost effective? Now you have several generations of ways of doing that. Some could be a solution like amine, others could be a sorbent. I also have different ways of capturing that. So we're doing demonstration on that to evaluate it. Maybe it could be solvent, could be some other solutions, could be even some other advanced technologies. And we also look at the disposal of it. What can you do? Can you utilize it? Or can you, if you can, long term, can you reduce the monitoring cost? Right now, we really don't know, when you put a large amount of CO2, under the ground and it's a long-term effect, what is that going to be? So we don't know. So we're doing a lot of research in those areas. Now, also from the power generation standpoint, can we really look at those fleet efficiency? Right now, a lot of them are really, really low efficiency. So maybe we could convert them, all of them, to supercritical, or could be something else like what we are doing here at IGFC. You have an integrated fuel cell into it. That could be maybe dramatically improve the efficiency out of it. So those are the things that we are trying to do at NICE. And like I mentioned, we have a slipstream test facility. We look at it, all kinds of different, even partial absorptions, capture partial of the CO2, so looking into different technology that can really address this CO2 issue, right? And then today that mentioned it to Chris and Chris's team that we also have a huge demonstration on the sequestration in Erdos Basin. We inject about 300,000 tons of CO2 under the ground, and which is actually is very low permeability basins. So we don't know a lot of them. But certainly we want to know it, because if this is a demonstration, how we're going to scale up, what about other basins? Can we use the same technology, and so on and so forth. All right, last but not least, that I put this summary here. You can see that rapid economic growth that is really put a lot of grand challenges for all of us, particularly in the energy sectors, right? We often feel like technology would be one of the key to resolve those issues. And the NICE, as a research organization, we are well positioned to trying to address those issues from technology standpoint. With that, I be happy to answer questions. I don't know, how am I doing with the time?
Pretty good, actually.
Yeah?
So if there's any enthusiastic student volunteers, I've got a couple of roving mics here. Otherwise, people will have to speak up. Okay, so if you show of hands for questions, and that looks like an enthusiastic student. There are volunteers and there are volunteered. While we're organising that, I'm going to ask a question. There was one figure that I found pretty alarming, and that is your projection for 5.5 billion tonnes of coal equivalent in 2020. And I think this is something interesting for us. A lot of information comes out of China, and we can never be sure about the reliability. But I've seen lots of stories and headlines about peak coal, so-called peak coal in China, of something in the order of 4 billion tonnes of coal equivalent, which you're nearly at now. And so my question is it really in the central planning to see 5.5 billion tonnes of coal equivalent, or do you think that's business as usual trend and energy productivity gains will stop that happening?
Yeah, there's a lot of people saying that, but we got those numbers because by we projecting that, you look at the GDPs. Actually, I have another slide that shows that everybody pretty much follows the same way. When you have certain GDPs and a certain populations, no matter whether you were at the beginning was in U.S. or Australia, they all pretty much, even Russia, all pretty much follows about the same trend. You know, people could argue that, well, with energy saving, it might be less. But the previous data point the other way. You know, if the GDP reaches 10,000 or a little bit higher USDs, and then you have the population, you know, closer to 1.45, that's the projection number. I think as accurate as it can be.
Mm. So raise your hand if you have questions, because I've got so Lynette at the back. And while you're taking the thing, another question about peak coal. Is it peak coal or plateau coal for China, do you think?
It's probably more like a plateau coal, yes. Okay. Yes.
Hi.
Go ahead.
Lynette Molyneux from University of Queensland. Forgive me if I've mistaken something, but it struck me on one of your charts that based on current reserve to production ratios, there was maybe a 35-year lifespan for coal currently. Did I read that incorrectly?
Probably more than that, you know.
Well, at 3 to 4 million billion tons of oil equivalent, according to